We're going to start by talking about the first law of thermodynamics. First law is merely a statement of energy conservation, but focused on the internal energy of a system, so the thermal energy that's trapped in motions of the molecules inside, for example, of a balloon. Okay, so we know that the system has a certain amount of internal energy. And so let's imagine I start the system with some initial internal energy, and then I can add energy to that system. And we're going to categorize the additions of energy in two ways. We're going to talk about adding heat to the system, okay, which, put it on a Bunsen burner and have a flame under it, injecting energy via heat. I can also add energy by doing work on the system. So, for example, I take a balloon in my hands and I compress it. I'm exerting, I'm spending energy to compress the balloon. That energy will go into eventually the internal energy of the balloon. So I add heat, I can do work on it, and this will result in a new final internal energy. Okay. Another way to write this, of course, is I can just say the change in internal energy is due to the addition of heat and any work I do on it. Okay. All right. So I've written this as Q plus W. The book chooses a different convention, which I don't like, but I'll stick with it just to avoid confusion. So this is the last time I'll write Q plus W. So this is the heat that flows into the system, Q. Let me not make a Q dot there. Heat flows into the system. This is the work done by the outside world on the system. So in these cases, being positive, those two numbers being positive, should increase the internal energy. What the book does instead is considers the work, leaves the heat the same. So it says, okay, heat is positive, it flows into the system. But it says, let's consider the work done by the system, not the work done on the system. Okay, so what this means is I consider the work done by the gas on the outside world. So if I'm blowing up a balloon and the balloon is expanding, the gas in the balloon does work on the outside world. It has to push the atmospheric pressure gas out of the way as it expands. Okay, and so in that case, the gas is spending energy to do that, and so the internal energy of the gas is going to go down in that case because I spent energy to blow the balloon up. The balloon blew itself up. Okay, I'm not thinking about the case where I'm blowing in. That's a different scenario. But imagine I take a balloon that's closed and I move it from a region of atmospheric pressure to a region where the pressure is lower around it, and then it's going to expand. Okay. So as it expands, it's going to do work on its surroundings and give up energy. Okay, so this is the convention the book uses is that this W is work done by the system. And that, therefore, you have a minus sign. Okay, by system. Okay, and the W that's consistent with this equation is the work done by external agent, let's say. External agent. Okay. All right, we'll stick with Q minus W, but just keep in mind, as with anything in this class, you can get the sign right by just thinking about it, okay? If you know what should happen to the internal energy because of a certain process, you can get the sign right every time, okay? So you'll find you will get an expression for the work, and then you just got to get the sign right. And so it's a perfectly acceptable strategy to just know how to calculate the work, whether it be work done by the external agent or the work done by the system, and then just make the sign correct so that the internal energy does what you expect. Okay, for example, if I have a gas that's in a container, this is the concept test we did in class, and if I push on it and compress the gas, I know that I've done work in compressing the gas, and that has to go into the gas. So the internal energy should go up in that case. Okay, and so if I look at this expression, that must mean that the work done by the gas was negative in that case. Okay, it fits perfectly well with this expression above, where the work that I've done is positive. I've had to expend energy, and it goes into increasing the internal energy of the system. Okay, all right, so I want to move on and talk about how to calculate the work. But before I do that, just one real quick statement, which is that, I've broken up the energy input into the system into Q and W. So Q is really an energy input in a disordered way. Okay, so heat transfer is really you take a hotter substance, okay, the flame underneath your from your Bunsen burner, and you put it next to something that's colder. And the collisions between the hot stuff, so the hot stuff has a higher energy per degree of freedom, and it collides with stuff that's moving around in a slower manner, and there's a net transfer of energy, but the transfer happens atom by atom. Okay, so there's no coherent process where all the atoms are pushing and putting energy in. They just collide randomly, and over time you transfer the energy. In the case of work, I'm considering an ordered input of energy where I'm moving. Say if I take the balloon and compress it, I'm pushing using the membrane of the balloon on the gas in kind of a coherent way. Okay, and so if you wanted to think about what's the difference between heat and work, it's a disordered input of energy. This is my point of view. Or an ordered input of energy in the case of work. Okay. All right, so let's talk about work on gases in particular. So we'll use this concept. Let me redraw that actually so I can be a little more careful on labeling. So let's have our piston here. Okay. And let's put a force on this piston, F. We're going to have gas inside with some internal energy. We're going to move this piston some distance, and we can call it little dx. Okay, so we're going to move it some distance. Let's assume this is a cylinder. It doesn't matter if it's not, but if it's a cylinder, let's define the area of the cross section to be A. Okay, now the work that I do in pushing that piston, I can write, let's write it as a little bit of work. Okay, so if I push it through a distance dx, I know the work that I do is F dx. Okay, and this is assuming that dx is in the same direction as the force that I exert, and therefore I'm pushing it forward and exerting and putting energy into the system. Okay, all right, so let me do this. I'm going to take you through this calculation assuming the point of view that's consistent with this equation up here, okay, with this one. So I'm going to do the point of view of the work done by me on the gas. When I'm all done, I'm going to switch the sign because that'll switch it from the work done by me to the work done by the gas on me, okay, which will be equal and opposite. All right, so I want to calculate this. And the way that I connect this energy input to properties of the gas is by making the following argument. What I'm going to do is argue that this process of pushing on the gas is what's called quasi-static. Okay, and this is a very important assumption that you should understand. Okay, when I say it's quasi-static, I mean that the system is in equilibrium, meaning the forces balance or nearly balance always. So I'm going to say that the force I exert is nearly perfectly balanced by the force that the gas exerts on the piston. Okay, so the force the gas exerts on the piston is going to be the pressure times the area of the piston. So the gas molecules, again, the way they exert a pressure is by bouncing off the piston, right? And so the pressure in the gas is transmitted through collisions with the material to push with the piston to push back. So I say that F is nearly minus P times A. So that means that the forces are balanced. Now, if that were really true, if it was completely balanced, F equals minus PA, the piston wouldn't move. Okay? There would be no acceleration of the piston. And I wouldn't accelerate the gas particles behind it as the piston moves. So this assumption really is that they're very nearly the same. And so the acceleration that's produced by the difference in the forces is incredibly small. But it's there, okay? So I'm able to make the thing move, but I'm not accelerating it very much, okay? Therefore the forces balance together. Now, the reason for this argument is that I want to consider a very slow process where I'm slowly inputting energy. because the way that I've written my equation is that I'm considering only the internal energy of the substance. Okay, that means the random thermal motion. I'm specifically not looking at bulk motion of the objects in response to a force. So the mean kinetic energy of the substance is not what I'm interested in. I'm interested in the random thermal energy. And so if you think about this process, as I push on it with a piston, the air molecules that are near the piston are going to be pushed to the right. Okay, so you're going to have a force that's going to tend to push these guys to the right. And they'll all be pushed to the right. Okay, so it's not as if I'm injecting random energy. I'm injecting directed energy into the system. Now what I want to happen next is I want to thermalize that energy. What that means is that this wind, so it's as if inside the piston I'm generating a wind. Okay, but what I'm interested in is, again, a situation where on average the gas is stationary, but I have random motions in the gas. The way that I do that is via collisions. Okay, so these gas molecules that get pushed are going to transfer energy to other gas molecules via collision. So they'll collide and the energy will be shifted into other directions. Okay. Now the momentum has to be conserved too. So if I do inject net momentum into the gas, I need to rely on the container walls to take that up. So the gas molecules will collide with the container and the momentum that I've put into the gas can be transferred out that way. Okay. But the energy gets transferred into the random thermal motion, and that takes time. You have to wait for collisions to happen. So I consider this process to be slow enough that there's really, as far as I'm concerned, a direct transfer of the work that I do by pushing the piston directly into the temperature or into the internal energy of the gas. Okay, it may not change the temperature, as we'll see. It depends on the boundary conditions of whether it's insulated or not, and so forth. But the energy goes into thermal energy and not into directed motion. Okay, so I spent a lot of time on that, but I think it's important to understand where that assumption comes from and that it's an approximate one. Okay, so what I can do now is say that the little bit of work that's done by me is then, instead of F times dx, I can write minus PA dx because those forces balance. Okay, and now what I can do is recognize that this quantity, A times dx, I should have another drawing of my piston here. Okay, so A times dx is the little bit of volume here. Okay, so this is going to be, A is in this direction, dx is this width. I multiply A by dx, I get the volume of the cylinder that I have basically changed the volume of the gas of by moving the piston. Okay, so this is going to be minus P times the change in the volume caused by moving the piston. Okay, all right, and so therefore for a process where I compress a gas or expand a gas by pushing on it, I can write down that the work that I do in that process can be written as the integral from the initial volume to the final volume of P times dV. Okay? All right. And again, I write volume with V as V with a slash through it for reasons that I can explain, but I won't do so here. Okay, so that's the expression for the work done. We call it PDV work. Now again, this is the work done by me, done by the external agent. Now, if we use the convention that the book does, the work that's done, we want to know the work done by the gas on the piston. And that's going to be the opposite of this. So the work done by the gas, and let me just, to be clear, I won't do WG from now on, I'll just call it W. But the work done by the gas on the piston in this process is just minus that. Okay? Okay. All right. So now the sign of this should be consistent with, again, your intuition about what happens to the energy. So if I look at this, there's no minus sign here. So I better find that when I do this integral, that the sign ends up being negative in the case where the gas is compressed. Okay, because that will make the overall change in the internal energy positive because I have minus Wg in my equation. And that needs to end up being positive in the end because I know I'm putting energy in. Now, I can't prove that to you here, okay, because it depends on what happens to the pressure as I compress it. So I don't know what's going to happen to this unless I make some assumptions, okay? And so in the later lecture videos, I'll go through that. But let me stop here.